this is the electron configuration in the periodic table. This is basically what we did last chapter if you didn't use the diagonal off-bomb method. And so we're going to throw in a few fun facts with each family on the periodic table. So to review, what are the 4 possible orbital names? Good. S, P, D, and F. And how many possible orientations does the S orbital have? 1. Good. And how many possible orientations does the P orbital have? 3. Good. The D orbital would have how many? 5. Nice work, Cora. And the F orbital? 7. Good. So then how many electrons can each orbital hold? So when we look at orbitals, it's how many of the boxes, how many electrons can be in each box? Pardon? 2. We max out at 2. 1 positive spin, 1 negative spin. So then what would be the total number of electrons that can be held in the S orbital? 2. Good. So we take the 1 orbital times the 2 electrons. So what's the maximum number of electrons for the P orbital? 6. The 3 times the 2 is 6. And for the the D orbital, how many electrons? What's the maximum that it can hold? 10. And then the F orbital, what's our max here? 14. Very good. So just a little review from last chapter about the SPD and F orbitals. We are going to look at the periodic table, kind of put some names to locations. The representative or main group elements, are those elements found in which 2 blocks? So we're looking for S, P, D, or F blocks. So the main group elements are found in the S and the P blocks. So remember that the S block is right here, and the P block is over here. So the alkali metals are found in the very first group, so that would be the first vertical column. Every element in this column has 1 valence electron. That 1 valence electron makes those elements highly reactive. And they're especially reactive with water. Oh, that's not what we want on that line, sorry. Right here is where water goes. These metals, even though they're metals, they're very, very soft. Like soft enough to be cut with a butter knife. They have to be stored under oil. Otherwise, they'll react with the water in the atmosphere. And when they react, it produces a hydrogen gas. They also will easily react with nonmetals. What side of the periodic table were the nonmetals located on? Left or right? Right, very good. These elements in this very first column are too reactive to be found as pure elements in nature. So that means they will always be chemically combined with some other element. Otherwise, we would have vigorous explosions going on just randomly. The second group, so this would be in the second vertical column, they have 2 valence electrons. They are slightly less reactive than the group 1 elements, but they are still too reactive to be found pure in nature. So remember that the alkali metals, the group 1s, they were very, very, very soft metals. The alkaline earth metals are slightly harder than the group 1 metals. So those two groups comprise the S block. So the two anomalies here are kind of hydrogen and helium. First of all, hydrogen's an anomaly because it is a gas placed with the metals. And then helium is placed with the 8th group, which would indicate that it should have 8 valence electrons, but it only has 2 valence electrons. So there's anomalies to this setup, but there is some logic behind it if you look at their electron configuration. So what is the electron configuration for hydrogen then? It's in what energy level? 1. What block? SPDF, S. And then how many electrons does it have? 1. So the reason, oh, that was a crappy one. The reason that hydrogen, even though it's a gas and it's placed on the metal side, the reason is that it has that 1 valence electron like everything else in the first column. So it's based off that valence electron, not its state of matter. Usually placed with the alkali metal due to the electron configuration. Everything in that alkali metal column, their last electron configuration is going to be NS1, N being whatever energy level you happen to be in. So like potassium is in the 4th energy level, so it would be 4S1. So apart from having the 1 valence electron, hydrogen does not share similar characteristics with the rest of the group. So the reason for its placement on the periodic table is because of its electron configuration. So then, looking at the electron configuration for helium, what would we have here? 1s2, it's in the 1st energy level, it's in the S block, and there's 2 electrons being filled in that orbital. So why is it not placed with the rest of those alkaline earth metals? Because they would follow the same pattern, NS2. Studi?
Because it has a full valence shell.
Very good. The valence shell, or the outer shell, valence shell is full. Just like all the other elements in that 8th column, those are all full, or their valence level is full. So that is why helium is often placed with the noble gases in that last column, because it shares very similar characteristics. It has that full valence shell. It doesn't react easily. So then, talking about the noble gases, these are elements in group 8 or 18, depending how you want to look at this. So the periodic table has your S block, then your transition metals, and then we have the P block. So sometimes we skip the transition metals here when we number the columns. So sometimes this is numbered 1, 2, and then the boron column would be 3, carbon 4, and so on until we reach the noble gas column, is sometimes referred to as 8. So these elements in the noble gas column are almost completely unreactive. That means they don't combine with other elements. They're very boring. They don't do anything exciting. Why would that be? Because, good, Daniela, because of the full valence shell. Having a not full valence shell makes elements reactive. So if it's full, the valence shell, there's no reactions. There's no electrons to do anything exciting with. So working backwards, Elements in group 17 or 7. So this one would be right before the noble gases. These have 7 valence electrons. Unlike the noble gases, these are very, very reactive. Again, what makes them very reactive? How many electrons do these halogens need to have a full valence shell? 8. So the desired valence electron number is 8. The halogens are at 7. So it is very, very easy for them to pick up an electron from another group of elements or another element. So it's 1 electron short of a full S and P blocks. And that makes it very easy for it to react. A couple interesting notes about some of the elements as halogens. Chlorine and fluorine are gases. Bromine, however, is a dark orange liquid. Iodine is a dark purplish grayish solid. And the 85th element, At, there's not much known about it. Not much known. And it's very rare. So looking at the transition elements, so the transition elements are in this middle D block. Here, they're found in groups 3 through 12. And the D sublevel is, remember, in a lower principal energy level than the S level before it. So if we're in the 4S level, what D block would we be in? 3D. Good. Similar properties as groups 1 and 2 because of having this S block full. But they're less reactive because this has the 2 valence electrons in it. Lanthanides and actinides, these are the 14 elements from cerium to lithium. They have a partially filled 4F sublevel. These are metals, and they will react very similarly to group 2 elements. The actinides, these are elements from thorium to lawrencium, and they're partially filled 5F sublevel. These elements are radioactive. And only the first 4, so AC, TH, PA, and uranium, have been found naturally occurring. The rest of them in that row have been man-made. Sometimes the lanthanides and actinides get referred to as the intertransition elements because they're the group together. They're the ones that get pulled out. Why does this F block get pulled out again? Yeah, so it's really just a formatting option. It's so we have it on one page, so everything fits. All right, so let's try this without looking at a periodic table. Name the period, the group, and the block in which the elements are located and the number of valence electrons. So kind of maybe make a table for the group, the block. So block, I'm meaning SPDF, and the valence electrons. So for letter A, what period would we be in? So by period, pardon? The fifth period, good. So we're looking at that number. What group? No, P is for block, but you're correct that it's P. How did you come up with 6?
We got the first two in the S block, and then I covered it'd be
5, okay. But we can't discount the D block that's represented there either. So you're on the right track for adding the 2 and the 3 up here to get 5, but we also need to incorporate this 10 in the same manner. So we add up all of these electrons and we'd end up in the 15th block. Or sorry, 15th group. And then valence electrons. How many valence electrons does this element have? 5. How did we get 5? It's in the 5th group. How else could we figure out 5 electrons? 5 valence electrons, sorry. Morgan? Yeah, we look at the highest energy level over here. So that would be the 5s. And there's 2 of them, and the first one has 2 electrons plus the 3 electrons here to get 5 total valence electrons. Does that make sense? Okay. Letter B here. What period are we in? Look at your last one right here. 7. Let's look at the block first. Maybe that'll help. What block are we in? Nope. If it's not S, what's our only other option here? It has to be the F block. Why are we not in the S block? Pardon? Because which one isn't full? No, you're on the right track. Okay. So what Marta, I think, is starting to say is if you look at this F orbital, is that orbital full, or is that F block full with electrons? No, because it can hold a maximum of 14. And so remember that S block fills first, and then you go to the F block. And so the element that we're looking at is actually in this F block. I'm not going to worry about grouping in the F block since it gets pulled down and set below the periodic table. It kind of makes it messy to figure out which group that's in. So then let's look for the number of valence electrons. 2? Anybody disagree or agree with that? What's the highest energy level for this particular example? Energy level. 5 or 7? 7. And how many electrons are in the 7th level here? 2. So that would be your valence electrons. Okay. What period for letter C? 4. What group? 2. What block? S. You only have that as the option. And then how many valence electrons? 2. Okay. Looking at D here. What period are we in? 6. What group? Not 6, no. For group, is your F block full? Yep, so we don't need to worry about that. How do we know that F block is full, first of all?
14.
It has the full 14. So then, looking at the 6S, the D block is one behind, so that makes sense, right? That's 5. So then we count across. There's 6 elements here and 2 elements here. So our group would be the 8th group. What block are we in? D. How come we're not in the S block here?
It's full.
Because it's full, and is our D block full? Nope. And then how many valence electrons? Okay, so options that I've heard right now are 6, 8, and 2. Okay, so Daniela's arguing that the correct answer is 2 because it has the highest energy level. Okay, Marta's agreeing. Leroy, does that make sense that 2 is the correct number for valence electrons on this particular example? Okay, good. And that is it for notes. One kind of maybe helpful hint is when we're dealing with any elements in these transition metals, their valence electrons always come from that S block before it. So almost every time they ask you for a transition metal's valence electron, how many will it have? 2 from the previous S block. So we'll learn later on that transition metals have various numbers of valence electrons, but for now we can operate that they have 2 valence electrons.